All right, here we go. Ignition system fundamentals, take two. None of you actually got to see take one because this dummy forgot to hit record on sound. So here we go. Um, I'm just going to kind of go over how an ignition system in a gasoline engine works, talk about a lot of stuff, get comfortable. It's going to be a while. So we're going to start off first just drawing a basic, very, very basic ignition system. And from there, it will build. Trust me, it will build. Okay. So first of all, of course, ground of the battery side. That's essentially just meaning that's going to be your engine block, your uh, frame, the body. They're all connected to ground. And then from the positive side, at least for this part of what we're dealing with, the traditional term here, this would be your ignition switch, and it's actually going to be an ignition switch in this, literally, because the ignition switch is the main device that's going to provide power to our coil. And so the ignition switch, when you turn the vehicle on, that provides your 12 volts, that provides your power to your coil in your ignition system. And uh, you don't want the coil to be on all the time, right? So then there's going to be another switch on the ground side of the circuit, and that switch will be your switching control device. I'm going to call that one. So now the switching control device, I'm going to go over a bunch of different styles that existed over the years and some of the theories on them. But essentially, this is your points in your old distributor, your ignition control modules, your powertrain control module, whatever is going to be in charge of turning on and turning off your coils, because that has to be done at a very precise and correct time, as you know, for the proper operation of the vehicle. So you have your ignition switch, which will provide the main power to your coil, and then you're going to have some sort of control device on the ground side of your coil. And that is basically what we're going to call the primary side of the circuit. Now, on your spark plug side of things, you have another coil here, and that coil is going to be considerably more winds and wraps in it. And the idea of this is this unit here. I guess I should draw that in black, would make more sense. Yeah, there you go. This unit here is actually your ignition coil, right? So, so if this is your actual ignition coil, um, the there we go. Um, you have on the one side of your ignition coil kind of your 12 volt side, and the other side of your ignition coil is where you have like your big spark plug wires and your spark plug and all those great big high insulation type of things, right? So I'm going to draw it a little simpler, like. Okay, I'm going to draw it almost backwards for you so it makes a little better sense. Um, anyways, realistically, a spark plug does operate backwards, but what I'm trying to draw here is on this side over here. This is your super high voltage side, so this would be your secondary side of the circuit. So essentially, your primary we would consider the 12 volt side, and your secondary will be your spark plug side, sparky side. Sparks is going to burn you. Um, so some of the features of this is if you need to get a whole bunch more power out of your secondary for the spark plug because uh, this area there, that's a gap, right? Like that is your spark plug gap, and the spark plug is grounded out to the engine block and will go right back to the ignition coil there. So, whoa, I didn't want a ruler. A ruler just kind of appeared there. There we go. There we go. Got that solved. Um, so that spark plug gap, that that's a big gap, and electrons don't particularly want to jump gaps, and they're not capable of jumping gaps easily. That's for sure. It takes a huge amount of motivation, just as it would for a bunch of humans. Take a whole bunch of motivation for you to jump over a large gap, right? So um, so the motivation, voltage wise or electricity wise, is voltage. And on your primary side, you're kind of limited to this 12 volt range, where on your secondary side, you have to get to a considerably higher voltage. And just for a range type thing, to jump a gap in a spark plug is anywhere from 3,000 volts up to about 15,000 volts in normal operation, like in just everyday operation, require that kind of voltage. And we'll talk about where that voltage changes for the most part. Um, and because it requires that huge voltage, well, your battery, if you recall, it's only 12 volts, so 12.6 at full charge. That'll become a little bit more important. And when the battery is charging and the engine's running and the charging system is operating, so when the battery is in a charged state, you're going to be around 14 volts. Meanwhile, when the battery, let me just get that out of the way. Meanwhile, when the battery is in a cranking state, meaning when you're turning the engine over and you're trying to start the engine, especially in a really cold day, thick oil, your battery's already compromised because it's cold as well. Sometimes you can get in around the 10 and a half volt range. So 10.5 volts during crank. So, and then at rest. So now we're in a scenario where on your primary side, you kind of have a little bit variable voltage. And this becomes important later on in the conversation when we're talking about the coil and heat in the coil, and we dwell on that situation. And in order to get the super high voltage in the secondary system, we need to have a transformer, and really that's what an ignition coil is. It's a form of a transformer. So what takes place here is you have a 12 volt system, and then in the primary side of the coil, so kind of in this area here, so I'm just going to identify that with a 1, and you'll see why shortly. So in the primary side of the coil, you're going to have some features of the coil where the coil is going to be it's going to be thicker wire, and it's going to have higher current, and it has that higher current because of the thicker wire. But to accommodate the thicker wire and the higher current, there's going to be fewer turns. And when I say turns, that's when you have a wrap of a coil, that's how many times the wire will wrap around the coil. So the primary coil has these features to accommodate the ability to create a big magnetic field because you need that current in order to create the big magnetic field. So if we get back to here in the primary side of the ignition coil, you've got a feature where it doesn't have very many turns. It doesn't have, a lot going on there, but it does have a lot of current going through it when it's operating. And then when we look at this one here, the secondary coil, so secondary coil, there's going to be many, many, many turns. Uh, and I'm going to use a base number of around, let's say, 250 times more turns than primary. So if you think of coil that's kind of in the same realm of the primary and the secondary in that coil pack. They both exist in the same coil pack to get something that's going to have 250, maybe 400, maybe 500 more turns. It depends on the build of that transformer or that coil system. Um, to get that many more, it's going to be a small wire, very thin wire. So you're going to have a thin wire for it to get that many turns. And in having a thin wire, it's going to have high resistance, so very low current. So these are the features of your secondary coil. Many, many, many more turns than the primary, very thin wire, very low current. So we have a scenario here where inside the ignition coil, you have the primary coil and the secondary coil, with the secondary coil having around 250 times more turns in it. And so just the features of the coil here. So I'm going to get them. So the features of the coil, if you have something that has 250 times more turns, that means the secondary, so the secondary system will have 200, oh, that's supposed to be a 5, mess that up. We'll have 250 times higher voltage as well as 250 times lower current. So the amount of turns that the coil has will multiply the voltage, but then will compromise the current. And this is again just a feature of a transformer. Like if you think of even your transformers that are sitting on the power lines that are delivering power to our houses, as the magnetic field and as the line voltage dissipates just through the natural transmission of kilometers and kilometers of lines, uh, the voltage starts to deplete. Well, they have to maintain a fairly stable voltage so you can have a transformer that will increase the voltage at the compromise of current. However, if there's sufficient, well, it doesn't matter. If there's sufficient wattage, there's sufficient wattage. If you get it, you get it. But realistically, this is how the ignition coil works, as do many of your transformers that are modifying voltage. They do so at either the gain or the compromise of current in the opposite direction. So your voltage and your current, if you multiply them for your wattage, shouldn't change unless you lose some of that energy to heat. And we will talk about how the heat is managed in there. So, so inside your ignition coil, you also have, oh, there we go. Inside your ignition coil, you also have a fancy little a fancy little deal like this blue thing here, and this would be your laminated iron core. So I'm going to call that number 4, and then we'll give ourselves some room. So your laminated iron core is a couple things. It's First of all, it's going to be just a great big chunk of steel. And iron, if you recall in chemistry class on the periodic table of elements, is Fe for fair, or being a ferrous material. Um, so to be a ferrous material is a material that enjoys or will readily accept magnetic fields. So the the iron core loves magnetic fields, and magnetic fields love going into the laminated core. And it really is a secret inside the coil, because you have this laminated core inside the coil. And if it were just a core, like the lines of flux from the magnetic field would come in there, and they might get a little zigzaggy, which means when this one comes in, it gets pushed in and crunched in, and they create a little friction amongst themselves. And so we don't want to see that, right? We don't want to see friction amongst magnetic fields when we're trying to concentrate a magnetic field. So they take a bunch of laminated plates and they glue them all together. And those laminated plates almost act as driveways for the magnetic field to come in. So the magnetic field, I'm going to just write that mag. So the magnetic field can enter into the laminated iron core, race through it in their racing stripes in the laminated bit, and then exit out of the iron core back into the coil from where they came. And this helps concentrate the magnetic field exactly where it should be. So what colors did I do? Blue and black and red. Holy jumping. I can figure this out. So if we were to look at this as a coil, we'd have the power coming in, from your ignition switch, right? So your ignition switch. So you'd have power coming in from your ignition switch, and then you'd have this great big primary here that's living on the outside here, and then it would have some sort of control device, switching device, so your points or your ignition control module or something like that, which will then control the ground side of this circuit. Hold on, give me a second here. Okay, and then on your secondary side of the circuit, you're going to have, um, I'm going to have to just write through the words, but that's fine. You'll get it. You're going to have your spark plug terminal where you're going to attach your spark plug wire, and then it's going to go around there, and then it's going to be like crazy busy like that, right? Lots and lots and lots and lots. I can't. Might as well finish it. Finish what you started, Matt. You know, you made your bed. You can frickin' lay in it, right? And then it's going to connect um, back to the block or back to a ground somehow, right? Connect itself back to the block essentially. So what takes place is you have your big spark plug boot, big spark plug boot coming off. That wasn't a very good drawing, but not a bad drawing, I guess. And then it's going to go over to your spark plug, which is it's going to have a big ceramic housing to it. So, and then again, there's a big boot over top. All of these boots and all of this is really just to insulate these electrons from jumping, because again, you're going to have thousands and thousands of volts coming in here, right? So you have your spark plug, and then hold on. Oh yeah, not a bad drawing. And then in the middle, connected to this, insulated from all of these things. Sometimes you'll have a resistor pellet in there. I'll talk maybe about that. So maybe all those things out to that little electrode right there. And then this is, oh shit, I hit the eraser and I really didn't mean to. After all that too, I was pretty proud of that whole deal. I guess I didn't completely destroy it. Okay, I'll try to do this without hitting the eraser. Okay, and then this, the spark plug itself, is bolted to the block, which will be your electrical return path back to the coil. So of course the block can handle all those extra electrons and all that movement in there. And so the biggest difficulty really becomes, how are the electrons going to jump that gap of the spark plug, right? That's a huge, huge, huge gap, and it's going to require thousands of volts. Well, the trick really does come inside of um, the coil and inside of this laminated iron core. So when you turn your vehicle on, you're going to close that ignition switch, and as you close that ignition switch, right, it's going to send battery power to the ignition coil. The coil, through the primary, then has to determine what's going on with that switch and with the control device. Now, your control device is a huge conversation, and really is one of the largest conversations that's going to come with this whole thing. So I'm going to call the control device now, number 5. We'll go down here. I'll write number 5, and then I'm going to come back to it because I want to talk and finish about the magnetic field. Okay, so we get to this magnetic field that when you close the control device, it's going to end up building this magnetic field in and around the primary and going into the laminated core. And it's going to travel through the primary, through the laminated core. Now, the magic that happens when you have one coil wrapped intimately with the other coil in and around this laminated iron core is you have mutual magnetic induction. And that, there we go. So mutual, that was wrong, hey? Well, look at this. Mutual magnetic induction. So that essentially means, for all intents and purposes, that whatever magnetic field exists within one of these coils will absolutely and simultaneously exist within the other coil. So the magnetic field that is in the primary is also in the secondary at all times, bar none, without fail. So that mutual magnetic induction um, is the main basis of how the transformer works or how an ignition coil would work. And it is based on the difference in turns. So when you have a magnetic field building in that primary, that magnetic field is also building in that secondary, and you also have um, voltage being developed in the secondary at a compromise of the current. So that all takes place simultaneously. So as that control device closes and you build that magnetic field in the ignition coil, it has to build that magnetic field at cranking voltage of 10.5 volts, right? And then once it's able to do that, the engine starts, and then you get to a charging voltage of around 14 volts. Well, if you had something that could develop the magnetic field at 10.5 volts, if you increase the voltage, it would also increase the current, which will also increase the heat inside of the ignition coil. So you can't increase the heat without damaging the coil. So if you want a coil to function during the cranking voltage and also have a coil function correctly while it's running and driving down the road, you have to reduce the voltage or the applied time where the voltage is going through the primary for the ignition coil. And that has a lot to do with that control device is ensuring that it's only going to develop the correct amount of magnetic field at the correct time. And that is all the trick of the magnetic field there. So when you get that proper magnetic field and it becomes a saturated magnetic field, we'll talk about that more in a bit. Um, you end up with around, 250 times more volts in the secondary than you have in the primary. Now, the primary is going to run at around that 10 volts or at a lower voltage than operating voltage so that it can control the magnetic field and it doesn't get too hot. Um, in the new days, the control of that magnetic field to ensure it doesn't get too hot is all done with control device. So the control device in new, and when I say new, I'm talking like the past 30 years. So all I'm going to just say is electronic ignition. So in electronic ignition systems, this is done with a control device by controlling dwell. And controlling dwell means it's controlling the amount of time that current is flowing in the primary. Okay, so in the new systems, that's what has to happen. And your electronic ignition system will control the amount of dwell or the amount of time that current is flowing in the primary to ensure that it only saturates the coil and gets to saturation or close to saturation, and that's it. Doesn't have any more time going in there because if there's too much time that there's current flowing in the primary, it starts overheating and it gets too hot. And as the magnetic field is building, it takes a lot of energy to build that magnetic field. And that energy has to be maintained, and that energy has to be depleted and controlled, and that's the real trick of the ignition coil and the control device of the ignition coil. So in a very basic stance, when the control device is closed, current is going to go flow through the primary, magnetic field builds in the primary and the secondary. If the primary is running at around 11 volts, so I'll just say primary 11. So if the primary is at 11 volts and the secondary is 250 times more than 11 volts, now we're in the 300 volt range for the secondary. 1,000. So you're in the 3,000 volt range for the secondary at this point. Now, that's the operation of a transformer, but we still haven't gotten anywhere near we need to get with that enormous voltage of the 15,000 volts that's required to jump the gap in the spark plug. And not just once, it's got to jump the gap and maintain a spark for a considerable amount of time, like 1.5 milliseconds, right? So it's got a lot of work to do over that period of time, which requires a lot of energy. So you close the control device, you start building this magnetic field in the primary and the secondary, and as that magnetic field builds, it's really using a lot of that energy and capturing a lot of that energy into the magnetic field. So I'm going to give control devices a little bit of room, and I'm going to go for our magnetic field build and mutual induction. We'll call that number 6 here so I don't get confused. And I'll give it some space and I'll say, okay, number 6. So Magnetic field in a coil. So as you have a situation where you apply power to a coil of wire, the coil of wire is going to build a magnetic field. And at first, it's small, and as it pushes and pushes and pushes and pushes, um, it's going to get larger and larger. Now, if the magnetic field has to grow in an area where it's not as easily built, like air, it requires more push to build the magnetic field. If the magnetic field has to build around a laminated iron core, it will build the magnetic field faster, but it still requires a large amount of energy to build the magnetic field and to make that work. And in a relatively crude manner, I like to refer to this as like a weightlifter. So um, you have a heavy weightlifter lifting the dumbbells, and right at first, right when the weightlifter starts lifting the weight to build this magnetic field, the weight's down. Well, I went right to eraser again. Dumb dumb. So the weight's low, and I like saying you get low current here. Right? You got low current, and what's going to happen is the weightlifter is going to take some energy, and the weightlifter is going to lift and lift and lift, and it's going to be tough, and it's going to take a lot of energy to have the weightlifter lift that weight. But eventually you get to a scenario where it's I guess I didn't draw that good, but oh well. The weight is being held and hoisted above the head. It's a situation electrically where we'd refer to that as the high current. And in order to maintain the weight in the air, the weightlifter now doesn't have to hoist and doesn't have to lift it up, but can they just lock the limbs and brace themselves and can hold it. So what I'm saying, in order to build the magnetic field requires a lot of energy. But once the magnetic field has reached its highest current, based on whatever weight and strength that weightlifter is, and in our terms, that'll be whatever resistance and voltage is applied to that circuit, um, based on that will determine how high the current will get. And then once it's there, it requires less voltage or less effort to maintain that magnetic field anymore. The problem is once that magnetic field has been built, once it's been built, it has um, it has a lot of potential energy within it. Just as the weightlifter, once he's lifted in the air and holding weights above his head, there's a lot of potential energy there. And just like a weightlifter in an ignition coil, it takes all of that energy and literally just drops it on the ground. And when it drops it on the ground, the weights slam against the ground the first time, and then they're going to bounce two or three times, and it makes a horrible ruckus. And the same thing happens within the magnetic field in the coil. The magnetic field takes some energy to build, it takes some time to build, but once that voltage has been removed or is no longer applied, and you take that away, once you take that away, that magnetic field is going to slam back into that coil of wire, creating a massive amount of voltage. And that massive amount of voltage has to be dissipated somewhere. And in many, many cases, it's controlled through items of what's known as like clamping diodes or clamping resistors, or it might have a choke or some sort of um, condenser or capacitor or something like that. But if you imagine back to the realism of it, it's like a weightlifter. If the weights are held and hoisted above its head, uh, then in order to drop them in a controlled manner, it takes as much energy to control the depletion of the magnetic field as it took to build the magnetic field, unless you just get out of the way and let it drop, and then it will collapse and bounce. And eventually that energy becomes dissipated as it bounces out of it. But it's got to go somewhere. So in something like a maybe a little relay that you'd find in a fuse block, a little relay will have a system where it's going to have a coil, and then a lot of them just have a simple resistor. And then, of course, I'd be remiss if I didn't draw both ends. There we go. Okay. Okay. So like a relay, when this coil is energized and it builds that magnetic field, it's going to attract the switch, close that switch. As soon as electricity is turned off from the relay has to dissipate that huge magnetic field, and it puts a resistor so that it can dissipate within itself and get rid of that magnetic field within the relay itself. So that's known as a clamping relay. Sometimes they'll use diodes for the same purpose, just to allow it to dissipate within itself and then eventually to atmosphere in a controlled environment. If it didn't have that clamping resistor or diode in there, even a little relay will push out about 80 volts. Sometimes you see some of the GM vehicles have the air conditioning actuating clutch there for the air compressor clutch. Um, Sometimes there'll be a little diode symbol inside your fuse block, and that's the diode for the clamping diode for your air conditioning. And if you actually measured the magnetic field collapse in those, I mean, I've gotten a little over 500 volts in some of those, measuring that just with a simple multimeter. So I've had a lot of fun with that type of stuff. But serious, it can be pretty dangerous when uncontrolled. But the magnetic field collapsing in a coil is exactly what we want to take advantage of. Because when we get to a system like this, when, just going to get rid of this now. Okay, I guess I can, okay. Okay, so when the control device opens up the switch, that magnetic field will collapse in the primary, and the primary then will jump up from that 11 volts. Remember, the primary was at, whoops, I erased it when I meant to circle it. Way to go. I'm good at that, aren't I? Okay, so when the primary went from 11 volts and the secondary to 3000 volts, now with the collapse of that magnetic field, the primary is going to jump up, um, a couple hundred times higher than that again in itself, maybe jump up another, like 200 times higher, and might, I don't know, like just wild guesses when it comes to these numbers, because it all depends on the strength of the coil, right? If you have an older V8 engine, you have an ignition coil that's got to run all 8 cylinders. It's got to jump the gap within the distributor cap, and it's got to jump the gap at the spark plug, and it's got to do it 4 times per revolution, right? Whereas now, with a coilover plug type engine, you've got one coil that has to fire one spark plug one time every two revolutions. So it's a considerably different workload, 8 times as a matter of fact, right? Considerably different workload on today's coils from yesterday's coils, and we're better at making them, right? We understand magnetic fields and we measure them better and all that type of stuff. So the numbers I'm really just making up, but they're approximations that are reasonable. So your magnetic field collapse in your primary, might get to around a 500-volt range. And once you get into the magnetic field collapse in the 500-volt range, if you had a system where what was I thinking? Oh yeah, where it was like a 250 times coil, like I was describing here. Um, what you'd end up with is, in and around that 125,000-volt range. So your secondary system, I like writing the secondary in red. So your secondary, again, mutual induction, right? It's you have mutual induction. Whatever's happening in the primary is going to happen in the secondary. So if you have 250 times more wraps, we now have a potential of 125,000 volts. And that is more than reasonable to fire a spark plug, because as we discussed earlier, our secondary spark requires around 3,000 to 15,000 volts to jump that gap. Okay, now your switching control device and dwell. So dwell literally is the amount of time that current is flowing in the primary. And I'm going to write and erase a whole bunch of things here. So hopefully we got that. There we go. Okay, so um, in the end, if you look at a cylinder, um, you get your valves there, and then you're going to have some sort of spark plug right around the middle here. Got a Hemi, man. Um, you have you have two scenarios that we should be talking about, and the two scenarios are the piston coming up to top dead center, and excuse me, and inside the cylinder we've got a large quantity of air mixed with hopefully fuel vapor, in and around that magical 14.5 to 1 range, hopefully closer 13 to 1, so you're making a little bit of power and having a little bit of fun in life, and the piston's going up on your compression stroke. So as the piston's going up on your compression stroke, compressing that air fuel mixture, um, you're going to ignite the spark plug at some point. Now, the magic of this, if I can just redraw the cylinder, is you want the piston to be, so if we're talking crankshaft rotating this way, crankshaft rotating this way. There we go. Same engine here. You want the biggest push and the most pressure to be existing in this area and exerting the force of those beautiful nitrogen soldiers expanding, right? Like so you get all your your oxygen and your hydrocarbons coming in, right? And then you ignite them on fire, and those hydrogens dance with the oxygen and they go build some water, and then your carbon goes mixes and makes some other stuff that people complain about. And then the nitrogen is really the magic, right? Because the nitrogen will expand, and as it expands, it does the work and it starts pushing down on that piston. And you want that push, you want that maximum push to be in and around the 10 to 20 degrees after top dead center. And that will create the most power in your engine. And with it creating the most power in your engine at that point, um, a great thing. Now, the biggest difficulty is the speed of combustion. So, how fast this burns doesn't change, right? It remains relative, it changes slightly, but it remains relatively consistent, based on the big variable, which is how fast the engine is spinning, right? So your speed of combustion versus engine speed is no good. I don't have to write that. So essentially what I'm saying is if the engine is spinning very slowly, then you need to ignite that air fuel mixture, say 10 degrees before top dead center. So at idle, At idle, you maybe need 10 degrees ignition advance, which is before top dead center. As the engine RPM increases, um, you now have less time for the combustion, less time for the heat to develop and the nitrogen to expand and create that pressure. You still want the most pressure at 10 to 20 degrees after top dead center. That won't change. To make power, that's where it has to be for the most, efficient and powerful engine. So at idle, you get about that 10 degrees advance. As your RPM increases, so does your ignition timing. You need to ignite the air fuel mixture sooner and sooner and sooner and sooner and sooner. And so at max RPM, maybe 32 degrees advance. Now, that number is huge variable, enormous variable, right? This depends on so many different features of your engine. Like, is it, how is the air getting in? How much compression does it have? There's these really are just numbers thrown out there that are approximations. So you need to ignite the air fuel mixture sooner and sooner and sooner and sooner. The problem with that is it will move the pressure build curve larger and larger and larger and larger until it gets to a point where the on the compression stroke, you have your crankshaft pushing upwards and forcing your piston up, and you have slowly, as RPM increases, more and more pressure pushing against the crankshaft because of that additional advance. So, of course, that becomes a point where you cannot ignite it so early. Otherwise, it's going to be hitting it's going to be hitting the piston so hard that it starts damaging the piston and fighting against the crankshaft in itself. So the trick is you want to keep this to normal operation and stay out of some of the bad areas where you have pre-ignition. Shion. There we are. Um, and that's really what pre-ignition is. Now, if pre-ignition is from your ignition system, it's damaging because, again, it's pushing against your piston. It's fighting against the piston going up. And in a lot of turbos with low compression, when you're at low speed and you pin it, you're going to hear that because of the expectancy that it normally has pressurized air coming in. And when the turbo hasn't spooled up, sometimes that can be what you hear. And that's kind of that pinging or that detonation noise you hear. Sometimes it's because you have carbon buildup in the cylinder and there's a hot spot in the cylinder and it causes an ignition before it'll ignite the fuel before the spark plug intended to ignite the fuel. So there's different reasons for it. And the trick of the ignition system is to control it so that it only provides enough ignition time in advance to give you as much power as you can get without creating any damage into the cylinder and anything like that. And that's in modern engines, that's the constant battle of the NOx sensor. So the engine control module will constantly be advancing the ignition timing until it gets just a sense of that pre-ignition, and when I say a sense, like if if this is normal operation, it would sense it right here. You wouldn't hear it until this point. So long before your hearing or your ability to sense it would take place, the NOx sensor would be able to pick up that signal and it would inform the engine control module then to retard the ignition timing and back that off a bit to prevent that. And then the engine control module will advance it and the NOx sensor hears it and will ask it to retard it and back it off again. And it goes through that constant advance retard back and forth and back and forth and back and forth. So that is the big trick of the ignition timing. Now, if I'm just going to clear myself some room here. Okay, so if the ignition timing, there we go. If the ignition timing and the ignition control is late. Sorry, that should be an E. Um, if it's late, that means it's igniting the fuel late. It can't and the pressure on the piston, right? Like getting back to again this whole concept of 10 to 20 degrees after top dead center in the normal rotation of the crank. Um, if the air fuel mixture and the pressure in here is getting its maximum pressure late, it's going to have a weaker push on the piston. It won't be able to push as much. It's almost going to be chasing the piston as much as it's helping turn the engine over. And late ignition timing becomes detrimental to power and eventually detrimental to emissions. So if your ignition timing becomes too retarded or too late, You don't get that push on the piston that's required. Your flame front's late, and you're not getting any power, and you have more emissions, even to the point where you might have partial misfires and things like that. So you really end up into a scenario where it's all bad, right? You're making less power and getting higher emissions. Nothing good out of that scenarios. And the only time, because of the extra hydrocarbons and emissions that come out of this, and because the flame front's in the cylinder too long, and because of the lower torque, there is a time when an excessively retarded ignition timing takes place, and that's right at engine startup in modern vehicles, anyways. So at startup, um, they retard the ignition timing very, very intently to throw for several reasons to throw hydrocarbons in the exhaust, literally to create partial misfire, not full misfire, but partial misfire, and to have excessive hydrocarbons in the exhaust to heat the catalytic converter. So that's to help heat the cat at that point in time. Another reason that they do it is the flame front kind of sitting in the cylinder and not contributing to expanding the nitrogen creates more engine heat. So it will also help heat the engine. And as a side benefit, the engine's going to produce lower torque. So for the first minute or so that the engine is running in this cold, late ignition timing scenario, the engine's going to be producing lower torque. So those people who love firing their vehicles up in the cold weather and just throwing it into gear and just giving her nuts right away and just start flying down the road, the engine is naturally reducing the torque being provided to the transmission. So it really is saving the drivetrain and saving save me from myself, right? Saving people from hurting their own damn selves and ruining their own damn vehicle. Although sometimes you think maybe they should just ruin their own vehicle. Would help me anyways. So so your late ignition timing um, is all those things. Lower torque, um, more emissions, partial misfires, hydrocarbons, carbon monoxide out the exhaust, um, but in an odd way does have some benefit during startup, and probably one of my favorite times to listen to any vehicle because you fire them up and they really just sound badass for a little while, right? And then they just go to normal again and everything's sad again and normal. But for a few seconds, even everybody's vehicle, like even the little SUVs, for a few seconds, they almost sound good. They almost sound like real engines again. Okay, if the ignition timing is too far advanced, um, that's where damage occurs. And so so you don't want damage. And I'm talking, like piston exiting engine, right? Like piston, there's so serious big damage eating up pistons. You do not want your ignition timing too far advanced because it really is the flame front fighting right against that piston as it's coming up on compression, completely damaging it. Can't have that happen. So that's why you have, that old trick nowadays between a NOx sensor, and a PCM, where the PCM is going to try to advance the timing and the NOx sensor will try to retard the timing. Or it doesn't actually, it informs the PCM of a signal of a knock signal, and then the PCM will know to retard the timing. But realistically, that's the dance between those two items to ensure that ignition timing is always as advanced as possible without creating any negative effects to the engine. And also, interestingly, in the older diesels, and especially some of the mechanically controlled diesels, why they're so damn loud um, because that uh, fuel was injected and ignited earlier in the diesels to get the power when they needed it. So there was intentional pre-ignition in the diesels, and diesels knew they were going to pre-ignite, and they did it anyways. And in order to compensate for it, they just built the engines much, much, much more robust. And today's diesels, with the better fuel control, they don't have to have quite as much fuel enter before top dead center, which allows still that huge power to come out of them without nearly the pre-ignition that was inherent with the earlier fuel control designs. So that the newer systems now are like rock and roll quiet. Plus, you don't need as robust of a block because you don't have that pre-ignition anymore. So win, 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 win. Holy jumping, where am I at? Okay, that's the control device, and that's a lot of the big stuff with the control device. Yeah, that's where I was at. Okay, so we've built up this magnetic field. Um, we've gotten this huge, huge, huge amount of energy out of, oh, there we go. Got this huge, huge, huge amount of energy potential out of the secondary here, right? And now with that huge potential, um, we've got to do something with it. I didn't talk much about dwell yet. Yeah, I'm going to come back to that thought, and I'm going to go right on to dwell first. Now, um, so the control device, again, has to be able to fire the fuel at the right time. That's where I was. Has to be able to fire the fuel at the exact right time, and not just kind of the right time, the exact right time. And very, very much this is based on RPM. Very much it's based on RPM. So in order to control that ignition timing RPM, you need to collapse the magnetic field, or you need to open the control device at the right time. So to open the control device at the right time, we also need to build the correct magnetic field in that coil. And as that magnetic field is building and that current is going, you don't want the magnetic field to be at maximum for too long, because that's like making a weightlifter stand there and hold the weight above their head for too long. So you want it to be able to build the magnetic field and to drop it right away so that it doesn't have to do excessive work. So not only do you need to open the control device, because in the weightlifting analogy, that means you need to drop the weight at the exact right time. So you need to know exactly when to lift it, how heavy it's going to be, in order to drop it at exactly the right time, right when it's hot. Drop it when it's hot. So it's going to open the control device at the right time, which means it needs to close the primary switch, right? So I'm talking, this control device here, right? So it needs to open it at the right time, which means to close it at the right time would be building the magnetic field. So opening the control device at the right time would be collapse of the magnetic field. And then closing at the right time is dwell time, is dwell start. So essentially, you close the switch, dwell happens, you build the magnetic field. So the amount of time the magnetic field is building is dwell. And then you want to open it, have the collapse of the magnetic field, and that spark happen all at the perfect time. Now, unfortunately, dwell has been defined differently over the years, even though it hasn't really changed. So I'm just going to get rid of this altogether because now we're into dwell. So dwell's an interesting cat because it's going to be measured in two ways. It's going to be measured either in degrees of rotation or dwell is going to be measured in actual time or milliseconds. Historically, in the olden days, degrees of rotation was by far the way dwell was measured, and the reason for that has to do with. Let's see if I can do this. Not too bad, not too bad. Okay, so pretend this is pretty evenly six-sided anyways for a six-cylinder. So if this were a distributor and a distributor shaft, it would be turned by the camshaft, and the distributor shaft would be rotating this distributor cam on it, or um, the distributor shaft for the points here is what I'm getting at. Now, this distributor shaft, by the way, could turn either direction. It could go clockwise, could go counterclockwise, and I know that very well because I recall doing a tune-up on many, many, many Chevys over the years at the GM dealer, and then I did a tune-up on one Cadillac, and those of you who know, I will never forget doing that tune-up because that made horrible pops and fires and bangs and stuff out of the carb and stuff like that. And I realized that the distributor, in fact, turned the other direction, even though, the 18436 572 is fairly solid in my head. That I learned a couple things there. Um, One, don't be overconfident, right? Check yourself. Two, read SI. Right, definitely read SI, check service information all the time. Um, Anyways, historically, in a points, so this is kind of what I'm drawing here is an older point style ignition system. So the point style would have kind of a lever coming around here with a switch, and then a receiver there, and then there would be kind of a pad, maybe a felt or nylon or something like that, some sort of pad that would run against the distributor shaft. And this would kind of be spring loaded downward. So as the distributor shaft turned, the felt would ride on the bumps and it would bump up, and then the spring would pull it down again, and this switch would essentially open and close. And as the switch opened and closed, um, the close of that switch would be the beginning of the dwell time, right? Um, so when that switch closed, it's the same as this primary switch control device closing. So that switch would close during the flats of these bumps, or the flats of this cam, sorry, and it would close there, and that would be the start of the dwell. So again, primary close, dwell start, magnetic field building. Hopefully until it gets to saturation, or that maximum current and that maximum um, that maximum current and that maximum height there, like that's your saturation of the coil. So um, your primaries close, your dwell starts, your magnetic field starts building, and then as the distributor shaft starts turning, it's going to make contact with the bump, say, and it's going to open that switch, say, for that period of time there, right? And so this will be open, right? Open during the bumps there. And right when it opens, at point of open is spark, right? Like that's right when your spark occurs, right at that point of open. So historically speaking, I think I changed the I changed the pen. That's why. Okay. Okay. Um, so dwell then again, when you define dwell as the amount of degrees that the magnetic field is building, dwell would be the number of degrees of rotation between when that switch existed in its closed state. And you would measure this based on degrees. The problem with this is this was what was referred to as a fixed dwell system. And so this being a fixed dwell system, meaning the degrees of rotation never change for your dwell. But if your degrees of rotation never change, then that means when the engine is spinning at a slow RPM, then dwell is too long. You have too much current in the coil. heat, resulting in heat, right? And then at high RPM, you may not get enough magnetic field. So you result in this situation where in this fixed dwell system, when it's low, you can get too much current in the coil and the coil is getting too hot. And when you're going fast, you're not getting enough of the magnetic field to ignite that spark plug to get you your spark when you need it. So you encounter these crazy scenarios, where people were putting in two coils so that at low current, you just hopefully dissipated the heat, and then or sorry, low RPM, and then at higher RPM, hopefully having enough magnetic field between the two of them, or alternating one cylinder each time. There's lots of different strategies. Today's engines with coil over plug, that would be a crazy amount of time, and you would have way, way, way too much dwell, given these scenarios. So now what they do is they don't use the fixed dwell system anymore. They do now just in milliseconds, and they're able to start and finish the degrees of rotation in a variable manner um, using control modules now. So today's systems, and especially the modern systems, you get your crankshaft position sensor and your camshaft position sensors, and they're going to have a correlation between themselves to ensure that they're both talking to each other and operating really well. And then by having some of this understanding of engine RPM to the accuracy of even the acceleration and deceleration between the strokes of each cylinder, um, we're able to exactly control when to start the dwell in an ignition coil and exactly control when to end the dwell or open the ignition primary to ignite the spark plug. So so now, we have variable dwell when we're talking about degrees, because we can start and end it at different points in time in engine rotation. But we now have the ultimate goal of constant dwell time in milliseconds. And maybe not perfectly constant, but at least to the point where it's saturating the coil to the extent that whatever is required for the engine. So, at your lower RPMs, when there's less air in the cylinder, it's going to give less dwell and less time, and there'll be less of a magnetic field, but it doesn't need as much for the spark plug. And then at higher RPMs, it'll do more, and this will result in both energy savings of the module, energy savings and heat savings in the coils, and then also life of the plug will be longer because you're not throwing as much at the plug um, on an ongoing basis, right? You're able to limit that on an ongoing basis. So there we go, is fixed dwell, variable dwell, the whole control device deal there. Um, The only part I do like to add just quickly, in a point style system, in the old distributor style systems for the control devices, what you realize in that point switch, I guess I should draw a big one. And that point switch, it's a mechanical switch, so it will progressively close and open. And when it opens and you get that collapse of the magnetic field, um, there's going to be a point of time where these two units are not touching each other, but are very, very, very close to each other. And at that point in time, you're going to have some of those minuscule micro effects of some arcing and sparking in between that switch. And that, of course, will eventually erode at that switch. So if the voltage in the primary gets too high, um, meaning you're not controlling the voltage well enough in your primary, or if um, uh, you're not able to control the magnetic field collapsing in this system, you do end up with that sparking and arcing inside of that switch, which damages the switch. And quite simply, electronically, here, quite simply, they're just going to attach this switch to a capacitor to ground. And then that extra voltage that comes from the collapse of the magnetic field, where the primary is, developing that that 500 volts that we saw here, in order for that 500 volts not to damage your switching device, the capacitor in this system, the way it's mounted would have been known as a condenser. So that one will absorb those volts, and then will actually assist the switch in um, helping charge the magnetic field of the primary in the next round when the switch closes again. So it not only protects the switch during the opening by absorbing the volts, when the switch closes again, it assists the switch in providing extra little push for that magnetic field for that primary coil there too. So that's a nice little feature of the older ones. In the newer systems, where we're using transistors as the switching device, the transistor is such a um, fast device and not a not a mechanical device. It's solid state, that they're able to build the transistors where, twofold, they switch fast enough that they're able to create a gap or a resistance large enough to not have any arcing take place. And then the other side of the coin, there's never oversaturation in the system, right? So just the fact that it can control how much magnetic field is built up in the coil is a protection device in itself as well. Um, okay, so now we're getting to a scenario where we got this collapse of the magnetic field. Uh, we're controlling the current in, and we're controlling the amount of magnetic field that gets built through the control device. The last thing is the to control the amount of current that's going through and to control the magnetic field. We also have to go back to an old thing that happened up here. We need to control that voltage as well. And again, in today's systems, that switching control device is accurate enough in order to control the magnetic field inside that coil. And it'll do it at any voltage because it understands the voltage, it understands the current, and it knows what the ignition coils can handle, and it senses heat. And they're just too accurate and too well controlled. In the olden days, they didn't have that well of control or that good of control that especially with the point ignition type system. So it's able to operate at crank, and then when the system fired up and the engine fired up, it would actually have too high a voltage, which would result in too much current in the ignition coil, too much saturation, especially at low speeds, and the ignition coil would overheat. So, to prevent it from overheating, they would design the whole system for the ignition system to operate at that nominal 10 and a half or 11 volts. And then when the system was in a cranking system, um, it would do a really different feed to the. So if this was our battery positive feed, and then this was our primary, so what it would do is it would send the battery feed straight to the primary through a switch that was engaged as part of the starter sequence. So as your engine starter was cranking over the engine, it would close that switch and provide direct battery power to the primary coil of your ignition coil. But again, this is only during the cranking sequence. So we're still looking at, 10 to maybe 11 volts in and around that range. So we're looking at a lower voltage. As soon as you release the starter, then that switch would open, and then there would be another circuit which would go through a resistor, and that resistor would consume in parallel with the primary, right? That resistor would consume around 4 volts voltage drop over that resistor, resulting in still 10 to 11 volts being applied to the primary. And that resistor was known as the ballast resistor. Again, as soon as we got into electronically controlled ignition systems, um, you didn't really require this anymore because we could control dwell time in and we can control the magnetic field, we could control the current, we could control the output. Everything's controllable, so it was no longer an issue that needed to be dealt with, just an old vehicle type issue anymore. So if you hear of a ballast resistor, that's what that's all about. Hold on one second. Okay, finally, finally, we have a scenario where we need, 3,000 volts to 15,000 volts to jump that gap from the spark plug, right? We need that to jump that gap from the spark plug. And in doing so, there's several areas that I just want to quickly talk about here, and I forget what number I'm at, so I'm just going to start with 7, which is going to be the high tension leads. So your spark plug wire, essentially. Okay, so your high tension leads, they're um, oh, come on, Matt, you can bring your carbon. Thanks. They're carbon string essentially. So it's not really like a solid wire. They're kind of a carbon impregnated string, which will conduct. And carbon conducts quite well, not extremely well, though it does have some resistance. So the natural resistance you're going to find in the thousands of volts. I've heard lots of different numbers in these ranges, but I've seen for some of these carbon impregnated style anywhere from 3 to 8,000 ohms per foot or per 30 centimeters. So uh, I believe the Alberta ILM state that number, and they'll say to a max of 30,000 ohms. Realistically, I've seen way higher resistance and I've seen way lower resistance because in today's systems, again, with electronically controlled systems, the system knows the resistance of the circuit that it's applying voltage to. Therefore, it knows how long to create a magnetic field in that system in order to not have too much of whatever. But anyways, I digress. These high tension leads, 7 millimeter, 8 millimeter, that's going to be their high resistance, and they've got a huge amount of insulation on them, right? Like if this was your 7 or 8 millimeter um, carbon bit there, then you might have like some sort of insulation layer right there, and then you might have, a bright green rubber or neoprene or silicone type of outer layer to the insulation, which is really protective and keep it from burning and melting and all sorts of stuff, right? You can get some pretty fancy ones, but electrically speaking, this is some of the important stuff. The rest of it, realistically, the rest of it just becomes how long do you want them to last? How well do you want these to be protected within your engine, and items like that. So those are your high tension leads. They can have reasonable resistance to them. They should have reasonable resistance to them. The resistance of the actual lead itself um, is not as important in this electronics or in the flow of it when it comes to the firing, but more important when it comes to the spark and the time of the spark for these. And I'll get into that in a second here. Nothing happens in a second. I think we know that. Um, the next bit here is kind of our spark plug, right? And spark plug, I know there's an enormous amount of detail that I could get into with the spark plug, but I'm going to try to keep it a little bit minimal. Okay, there's our ground, there's our electrode. So inside of the spark plug, so the spark plug wire caps on here, again, you're going to have some huge type of insulation to protect that thousands of volts that literally is intended to jump gaps, right? So you need to insulate it very well. Inside the spark plug, sometimes you'll see a resistor, not all the time. And then you get to the end of the spark plug. So the spark plug really is just again, think of it as a wire. Um, at the end of the spark plug, sometimes they'll put a precious metal there because the precious metals do not seem to lose as much of their material during the operation and during the normal life of the spark plug. And and so you have from the secondary, you have a gap to jump at this point here. And now inside the spark plug, You have this big porcelain insulator, and the porcelain helps protect the parts inside the spark plug. And from the metal, from the metal of the spark plug here, and in that area, really is the heat range. So if there's more of a gap there, if there's a longer gap, then it's harder for the spark plug to get rid of the heat. If there's less of a gap, then it's easier for the spark plug to get rid of heat. So what I'm saying is, if you have an engine that runs very hot, turbocharged, supercharged, you got high compression, um, high RPM, things like that. You have an engine that runs hot, you're going to want a spark plug that runs reasonably cold. Otherwise, the spark plug will create some of that pre-ignition and detonation and damage your engine. If you have an engine that's a very low power, you're going to want a spark plug with a higher heat range that will be pretty hot or have a big gap there, because you want the spark plug to get hot enough to burn off some of the coking of the carbon that'll come from the combustion gases and such, or the exhaust gases. So it has to be hot enough to burn off the carbon, but then also cold enough that it doesn't create pre-ignition. So heat range is very much specific to the engine and the engine build and stuff like that. And I digress a little bit, but becomes important in the spark plugs and such. Your electrical circuit here is really just the spark plug through there, but then it has to jump this gap. Now, when it's going to jump the gap, it's got to look at a lot of things. So, as a spark is jumping a gap, it needs a lot of pressure to jump the gap. But as it's trying to jump that gap and create that pressure, as it's trying to do that, right? It's going to really depend on the environment that it's living in. And some of the main factors that affect the spark jump in the gap is it, remember, it has to ionize, which is really the term to mean just electrically charge an atom. It has to ionize whatever is existing inside of that gap. And in this case, it has to ionize through air and fuel. Hopefully, just air and fuel. There'll be a little bit of water vapor, there'll be a little bit of contaminants and things like that. But for the majority of the items, it's going to be your air and fuel that it has to ionize. So, therefore, these things react differently, because to ionize air, well, the more air, the harder it is to jump that gap, or the more voltage that's going to be required. So, the more air is more kilovolts. And when we talk more air, the majority of the air is coming from your foot, right? You go to wide open throttle, it lets more air into the engine, it's going to require huge kilovolts. Likewise, at idle, you have less air, and it's going to require less kilovolt firing voltage. So your air is the single largest contributor to the voltage required for the spark plug to jump the gap. And when we get to that large range of 3,000 volts to 15,000 volts, that's what it boils down to. That huge range is because of the huge variation of air that will enter the cylinder, right? It'll run that big of a range mostly because of that. Now, other things that affect the firing kilovolts will affect the firing kilovolts, but not nearly as much as air. And I, cannot emphasize that enough. Air, 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 air. So more air, more firing kilovolts. Well, the other thing that's going to affect the firing kilovolts is fuel or fuel vapor. Now, just like lightning bolts in the rain, um, a lightning bolt is enabled by two things: by friction, in other words, the creation of this high voltage, so the friction of the clouds, and then the humidity in the air. And inside of a cylinder, it's no different in that scenario. Your fuel, if you have a large quantity of fuel, then that large quantity will require less firing kilovoltage to jump it because fuel is a good conductor of electricity. So if you have a rich mixture, you're going to have less or lower firing kilovolts. If you have a lean mixture, you're going to have higher firing kilovolts. Um, that's another major contributor to the kilovolts, right? So your air fuel, your compression, whether it's turbocharged, supercharged, right? You have a turbocharger. You might be going from 3,000 volts to 25,000 firing kilovolts, right? Like it could be a big difference. Um, so so your air and your fuel make huge differences that way. Some other factors that will come into play for higher and lower firing kilovolts simply become some of the mechanical factors in this system. So when I'm talking about that, I'm talking like if you have too high of resistance or an open in a wire. That'll cause an increase in your firing kilovolts. Um, if you have a grounded wire or lower resistance in the circuit, it'll cause a decrease in your firing kilovolts. So those work vice versa. Your gap itself, right? If the gap is large, will require a higher firing kilovolts. Speaking of higher. And if the gap's small, it'll have a lower firing kilovolts. If you have contamination in the spark plug, so quite often right in here, this area right in there, especially when I was talking about having too cold of a plug that it won't burn off the carbon in the cylinder, if that area there, that area would be referred to as fouling, and what that is carbon buildup. So that's carbon buildup right inside the spark plug. So the carbon buildup inside of that spark plug, well, carbon is a good conductor of electricity. So what would take place there is instead of the spark jumping from the two electrode ends or jumping the gap where it's supposed to be jumping, the spark plug would end up just traveling through the uh, the carbon and through the fouling inside the carbon, wouldn't really have to do any work, wouldn't have to jump any large gaps or go through much air, and it would find a quick route to ground and then not be an issue. So, carbon fouling, if you have a carbon fouled plug, it does result in a considerably lower firing kilovolts as well. So all of these small things also will affect the firing kilovolts, but really, as long as your gap is reasonable, and quite frankly, you should not have a gap issue. Like just talking as a mechanic, if you suspect a spark plug, check the damn spark plug, right? Like don't, you should not have a spark plug gap issue. Just check it and know, right? There's no, you shouldn't be wasting time and things like that. You get your P0300 into one or two certain cylinders, just check it, just check it. It's not worth wasting your time. Do a compression test on that cylinder. Just look at the spark plug, look at the wire, swap with a known good cylinder, see if the misfire moves. Like, don't waste your time on diagnosing these things. They're quick and easy. This is about operation, about understanding how the system works. So, so the all these different things do affect the firing kilovolts, but none as much as air, right? Like as much as how much air you're putting in there, and of course that compression, right? But compression realistically is how much air, and that quantity of air that exists only over that gap. Um, so when we're talking about the pressure required to get there, I guess did spark plugs. Now I'll go. Oh yeah. Finally, the return path here. The only thing to take note is, I mean, the return path realistically is um, there we go. Okay, realistically, the return path is the block, right? It is the engine block. So um, the return path is normally not an issue so long as your ignition coil has good clean connections, your control module has good clean connections, everything is nice and clean. And when I say that, uh, really pay attention to the threads on a spark plug. Uh, Gosh, don't coat them with things. That is the electrical path to ground for your high voltage and your high tension lead. So if you're insulating your spark plug to the block by putting paste in there, then all you're doing is hindering the operation of your own engine. It doesn't help at all. Okay. Um, Finally, I just want to get talking about this whole relationship of firing kilovolts and kind of understanding what's going on when you're looking at an oscilloscope pattern of an ignition waveform. So first thing to note is we're looking at secondary voltage, and this becomes, well, interesting anyways. So when we're looking at secondary voltage, and we just, I'm going to start a continuum, um, the whole process has to kind of take place here where you, I'm going to start it in dwell time, and dwell time meaning the primary switch is closed, um, the points are closed, it's the cams on its flats, the transistors open, the base emitter the base collector, sorry, or you know what I mean? Like, this is ridiculous. We could go far ways. Either way, we opened up the primary. There's the erase again. So as soon as you open up the primary, that huge magnetic field collapses. And again, that magnetic field of the primary induces mutually into the secondary. And the voltage in the system spikes up very, 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 very quickly, almost instantly. And it will spike up. And in that's the pressure building in your secondary system, pushing in to the spark plug here and just pushing into the spark plug. And that pressure building on until it gets to the point where it's going to jump that gap. Now, of course, the pressure required to jump that gap is based on all those variables we talked about, right? Now, how much air is in there, how much compression, how much fuel is in there, all the resistance of the system, the gap in your spark plug, how much fouling is in the spark plug, piles of variables that exist within the scenario determine the pressure. But once sufficient pressure has built up in the secondary to push across that gap, um, this is where, it's like the lifting of the weights. We've used all that energy to lift the weights, and then it can hold it up. Same type of feature happens. So once the pressure is built up sufficiently to bridge that gap, say, again, this is variable depending on where we're at in engine operation, and I'm going to just say 8,000 volts, right? So around 8,000 volts it took to fire the spark plug at this point. Now, if we looked at your ignition coil, as kind of a bucket, and I would say this bucket would have 125,000 volts available into it, right? And based on our math, that makes sense. We have 125,000 volts available in the bucket, and the system itself dissipates heat, so you're going to lose some energy to heat, right? The system itself requires some maintenance and all that, right? So let's say we've got 80,000 usable volts in here. Okay, so we've got 80,000 usable volts. 8,000 of those were used towards the firing voltage. So we might have around 72,000 volts remaining. Well, that voltage remaining, we want to consume, and still has to get consumed, right? Because that energy, it's still energy potential. And that voltage remaining becomes your spark time. Essentially, how long can spark be maintained over that gap? Because so far, all we've done is create the push to bridge the gap. Once that gap has been ionized, there we go. Okay, like, we've got a wire there, we've got a gap, and the the voltage is pushing and pushing and pushing and pushing and pushing, and nothing's happening. It's pushing and it's pushing until it gets again to enough voltage to bridge that gap, and then it's going to literally create a lightning bolt across that gap. Once that lightning bolt has been created and that area has been ionized, it will require considerably less energy to maintain that ionization, because now it's got path, right? Now the bridge has been built. So so it may have required, you know, 8,000 volts to push across the gap, but it may only require 1,000 volts to maintain current across the gap. But that's voltage over time, right? Because those volts are still flowing, and that coil only created so much, that bucket only has so much voltage available in it. As it's consuming 1,000 volts at a consistent rate to keep that gap ionized, it's going to deplete that bucket of available voltage in the coil quite quickly. So it will require like 8,000 volts to bridge the gap, but then it might only require 1,000 volts to maintain that spark time. Now, this becomes really interesting because as your firing voltage increases, so too your spark time shall decrease unless we change the available um, reservoir inside of the coil. So this is where I say that traditional systems, um, that was exactly what happened, and it was manageable. But at higher RPMs, things got a little hairy. Current day systems, they can control the filling of the bucket more accurately. And by controlling the filling of the bucket, then regardless of the firing kilovolts required, it maintains a more consistent spark time. And that really is the end goal, is to have that more consistent spark time at any engine RPM. But eventually what happens is, oh, what a mess. Okay. Eventually what happens is you run out of available voltage. You run out of available voltage in the coil, and there's no longer sufficient pressure to maintain that gap, and we lose it, and current drops off. But there is still pressure in the system. Again, think of that weightlifter. It took a lot of work to lift the weight, right? And then the weightlifter holds the weight, but when it drops, it still has to go somewhere. Even if they tried to control the drop and dropped the last foot, it still needs to be managed. It still needs to be controlled, and it's still going to bounce off the ground because that energy still exists within it. So, so you get a really kind of unique feature of coil oscillations. So um, coil oscillations is really the dissipation of the remainder of the energy within that ignition coil, because right at the point where no more current can flow over the secondary, we still have a situation where, oh gosh, there's no, where does my other drawing? Oh yeah, there we are. We still have a situation where this is not ionized anymore. We don't have enough voltage to maintain the gap, but there is still some pressure here. And if it can't go over that gap, it's going to send itself back. And then it goes back into the primary and back into the secondary and back into the primary. And this is that unique period of time where there's no current going through the primary and there's no current flowing through the secondary, right? So there's no spark over the gap, and the primary ignition control switch is open. So that dissipation, those coil oscillations are just a natural dissipation of the magnetic field within the coils themselves. And it is what it is. They're going to be, much larger if you have a big gap, smaller if you have a small gap in your spark plug. So the gap changes that a bit. There's a lot of diagnosis that can get involved with your spark line, whether it ramps up or down, and how many oscillations there are. There's a considerable amount of diagnosis with that. I'm not going to get into all of that stuff right now. I'm just talking the main observation of what a good system should look like. And then there's a period of time, I didn't intend for that to happen. Okay. Then there's a period of time in the system where there's really no activity, right? So this is open primary and no spark. And then I can also say low available coil energy. So essentially, this is the cool down time of the coil. This is when the coil gets to relax, stretch out, and get itself together for its next round of abuse. So it managed the dissipation of the magnetic field. We've got open primary, no spark coil, nothing like that going on. And then, whoop, 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 whoop. And then all of a sudden, we're going to see one more little decrease here. I'm going to get rid of some of this. Okay. And then we're going to see another little decrease here. And then that, if we were to follow this around, repeats itself right here, right? So this is the end and start of the event, because again, it's an event. It just continues and continues. So at this point in time, another unique thing happened. This is where we're going to start current in the primary. So start primary current, and we do that by closing the control, the ground path, right? Closing the control, whether it's your point switch or whether it's your ignition control module or a transistor, by closing the control switch, and it's going to start magnetic field build. So right as soon as that primary closes, in the primary circuit at that point in time is when the current is quite low in the primary, and then right as it opens, the current would be the highest, or when the coil is closest to saturation. But this is in the secondary circuit, and an interesting thing happens here is Sometimes you even may see little oscillations there as the primary will turn on as well. And the reason for that is when you think about this, we're looking at the secondary, which means when you're looking at the oscillations into the secondary, that is really the primary inducing into the secondary, where the secondary will induce back into the primary. This is literally you witnessing mutual induction. That's what it is. Um, so this is the generalization of the waveform when we're looking at it. So um, if we were to name the periods of time that exist within this period, I'm going to start with right here at this point. This would be our firing line. And then this point here would be your spark line. And then, of course, you have your coil oscillations and then a period of time of rest and cooling, which again, when you think about a V8 in the olden days running at 3,500 RPM versus today's V8s where it's a coil over plug where it can literally it has 8 times less work to do. 8 times less work and better computer controls. So all sorts of awesome. So today's coils can be considerably smaller, and you get just as much, if not better, activity out of them at at a lower workload for the computer. So today's ignition systems are pretty fascinating, really, when we look at it. And then, of course, here, right at that point, you would say your primary closes, and then here at that point, during this time period, we'll call that your dwell time. Is that time period there. And realistically, your dwell time, is between 1 and 2 milliseconds, depending again on all those factors of speed and coil and things like that. Um, well, that's about all I've got to say about that. I hope you enjoyed it.